Okay, so what happens when light strikes an object? Suppose I have a chunk of something down here, and I have one of these, traveling electromagnetic waves, or a little photon of light that's headed towards this object. What happens? Well, when light strikes an object, some fraction of the time it will bounce off that object. Some fraction of the time it'll get absorbed by the object. So maybe the light will have its energy turned into thermal energy of some of the atoms in the material jiggling around. So that's like an absorption event. And sometimes the electromagnetic radiation will pass right through the object. Right? So any one of these three things can happen, and in fact does happen all the time. So for instance, when visible light strikes an object that we perceive as blue, what's going on is that almost the entirety of the visible spectrum of light is being absorbed by the object. So any green light that's coming in gets absorbed, or any red light that's coming in gets absorbed. But blue light that's coming in gets reflected. And so we observe this object as if it's blue. Okay, and this kind of thing happens all the time. And in the next section, we'll think more about what happens when light tends to pass through an object. And in this section on mirrors, we're going to think about the process of light bouncing off of an object. Okay, so because the wavelength of visible light is so small, remember, just hundreds of nanometers at most. Another way of saying that is the energy of each photon is so tiny. Because of this, we can talk about the behavior of visible light using a particular approximation that's known as geometric optics. So we'll use a so-called geometric optics approximation. Okay, and in this picture of geometric optics, when visible light is traveling through the air or through space or through water or through glass, that light moves in a straight line between wherever it's coming from and wherever it's going. Interesting things only happen when light actually strikes an object. And in this picture, we basically ignore the fact that light has the capacity to interfere. So we never kind of consider the fact that there might be constructive or destructive interference of light. And so, for instance, as we're standing in a well-lit room, we just have tons and tons of these photons bouncing all over the place, crisscrossing each other's paths constantly. But we assume that the light rays that, for instance, are making their way into our eyes are not at all affected by all of the light rays crossing in front of or behind those photons that do make it to us. So all of these approximations are kind of not quite correct, but for everyday visible light, the degree to which those approximations are not quite correct is really minuscule, and so it's a quite good approximation. So to start out, we have light going between 2 points in a straight line. So for instance, if I have like a light bulb and it's radiating light, and here's like an eyeball, then light just goes in a straight line. And of course, I can't draw actual straight lines, but you get the idea. Okay. We want to ask now what happens when light hits different materials. So for instance, what happens if one of these rays of light, I don't know, maybe you've got a weird room that has a mirror on the ceiling. So what happens as one of these rays of light hits the mirror and then maybe can bounce into our eyeballs? What's going on there? Well, the simplest object is a flat mirror. Right? And a flat mirror is an object composed of a layer of glass on top of typically a silver background, or a material that's kind of silvered. So it's an extremely reflective substance that's silver, so that almost all of the incoming light bounces off. Almost none of it gets absorbed, and it can't pass through the silver like it can the glass, and so almost all the light gets reflected. What happens? What is the nature of the way that light gets reflected? So if I have a mirror down here, and I have light coming in like so, the way that the light bounces off is that the angle that the incoming light makes with the mirror is equal to the angle that the outgoing ray of light makes with that mirror. So it's coming in like this. I could have said that this angle is the same as that angle. In optics, it's traditional to make use of the angle relative to the perpendicular rather than relative to the mirror itself. And the way that these flat mirrors work is that the so-called angle of incidence, the angle of the incoming beam, is equal to the angle of reflection, the angle that this outgoing beam makes. Okay, so there you have it. When light strikes a flat reflective surface, it bounces off in the simplest possible way that it could have. Right. So if we're, for instance, looking in a mirror, we've got, say, a random photon, it bounces off of our toe, and the one that makes it to our eye kind of bounces off the mirror like so. Something from our hand bounces off the mirror like so. And we we see these rays of light. Our brain interprets them as if they're coming from, our mirror image standing over here. And in the lecture notes, I've done a much more careful job actually lining up so that this distance, the distance between our actual selves and the mirror, is the same as the apparent distance between our image and the mirror behind it. Right? So essentially, our brain perceives this scenario as if we're looking through a window. Right? Our brains are not built to. Our brains aren't kind of built to process the actual paths of these rays of light, and so when we see an object in a mirror, our brain interprets what it's seeing, assuming that light has kind of followed a straight path to our eyes from wherever this image came from. Right? The reason that we can see our reflections in a mirror, but we can't see our reflections in most things, even though light is bouncing off, this painted wall, or I don't know, one of those pictures, or this book, or something like that. The reason is that at the atomic level, most surfaces are quite rough. Right? And so surfaces actually look like something like this. And so, a ray of light will bounce off this mirror, and it will make a reflection relative to the angle of the thing that it's striking. So if this is like this, then this light will kind of bounce off like that. And if there's a nearby, beam of light, it might bounce off like this. Something over here might bounce off like this. And so light that starts out together ends up looking like, it's being redirected in all kinds of different directions. Equivalently, if I have not a mirror here, but like a flat wall that's just painted, then, a photon that starts at my foot might bounce off like this, and one that starts off right next to it on my foot might make it to my eye. And so because, rays of light that start out in the same place end up all over the place, not anywhere close to my eye, I'm not able to see actually an image of my foot in this mirror, for instance. Okay. This kind of scattering is called diffuse reflection. Diffuse reflection. The idea that nearby photons end up being bounced off in all kinds of different directions and end up in different places. And when you have diffuse reflection, you kind of perceive something as light because photons are bouncing off that object and making their way to your eyeball, but you're not able to see reflections of anything. In contrast, when you have a mirror and this thing is actually just a beautiful flat surface so that rays of light that start out close to each other end up close to each other, that's called a specular reflection. And that's the kind of reflection where you can actually see, an image of the thing reflected.